Thanks everyone for coming to today's seminar. It is my great pleasure to introduce today's speaker, Dr. Jonathan Delph from Purdue University. So Jonathan is a passive source seismologist, and his research focuses on creating. I can speak louder. So Jonathan is a passive source seismologist, and his research is focusing on creating high-resolution seismic images of crust and upper mantle. So he has worked on many different tectonic settings, including subduction zones, magmatic systems, and also cratonic crust. Jonathan got his bachelor degree from Arizona State University in 2012. And got his PhD from University of Arizona in 2016. And then he did a Rice postdoc fellowship at Rice University, pretty close to where we are. And then he moved to University of Oregon for another short postdoc before he started his position at Purdue as an assistant professor in 2020. So Jonathan has done some really interesting work at Cascadia subduction zones, and that is how I got to know him, and we will hear about this work today. So without further ado, take it away, Jonathan.
All right, thanks, Shuoshuo. And thank you for inviting me to come here and share some of my research with you. It's really exciting to be back in Texas. I haven't been here since I left Rice in 2019. And it's nice to get away from the cold weather in the Midwest that we're starting to experience. So today I want to talk with you about some research I've been doing over about the past 5 years, investigating how lateral heterogeneities in the manifestation of subduction are manifest in the Cascadian margin, and try to look for some mechanistic reasons as to why different variations might be linked together. For example, you can see on this figure right here, I'll try to use this laser pointer for the people on Zoom. One of the major lateral variations we see in Cascadia is the distribution of non-volcanic tremor. This is a process that takes place along the plate interface, we believe, between about 20 and 50 kilometers depth. And this shows significant correlations with topography in the overriding plate's forearc as well. And it's not clear why these two should correlate together. And these correlate with quite a few different geological and geophysical observables as well, more than just these two. So the goal of this talk is to try to find out how these different variations in the Cascadia margin are linked. I should say, I started this work back when I was a postdoc at Rice, trying to broaden out from my kind of PhD experience studying Tethyan domains and working in South America a little more, and Cascadia struck me as this really interesting example, because you see all of these different variations in the manifestation of subduction over a relatively short subduction margin. And I worked with Alan Levander and Feng Lin Niu a little bit with this early on at Rice, then moved to the University of Oregon to work with Amanda Thomas to get a little bit of a different perspective, more of an earthquake seismologist and earthquake mechanicist, so a little outside my seismic imaging and tectonics background. So a quick outline of this talk. I want to start by how we got to where we are in the Cascadia margin, very cursory overview, and then talk about how fluids are generally expressed in subduction systems. Then we'll look at what other lateral variations exist in Cascadia besides just this non-volcanic tremor distribution and overriding plate forearc topography. So the main way that we can try to link these things that are taking place near the plate interface with what we see at the surface is through creating seismic velocity images that can tell us about the crustal architecture between these two depth domains. So I'll briefly talk about the methods that we use to create a 3D model of structure along the Cascadia margin, in this case, specifically focusing on a 3D model of shear wave velocities. Then I want to focus on two main points, that is relating these shear wave velocity structures to subduction processes, particularly what's happening near the plate interface, and within the downgoing oceanic lithosphere, and then come back and link these deeper processes with what we're seeing at the surface. And the major takeaway I'd like you to have by the end of this talk is that there's a significant amount of interplay between the lateral heterogeneities that we see in Cascadia. And I think our seismic images present us with kind of the missing link that can relate these. You're good. All right. All right, so the Cascadian margin as we see it today has been operating for about the last 50 million years after the accretion of the Silesia terrain, shown by this blue polygon. I lost my laser pointer, it's okay. Keep this more simple. Shown by this blue polygon on the overriding plate. So this is what we think, this over-thickened oceanic plateau-like crust that was accreted onto the margin of North America. So relatively long-lived system, 50 million years is plenty long enough to develop kind of a more mature subduction zone. The downgoing oceanic lithosphere is characterized by very young ages, about 10 million years old at the oldest near the trench, about 5 million years old at the youngest near the trench. Really small variation in age in that downgoing oceanic lithosphere, and also a relatively small variation in subduction rate along the margin, kind of being at our intermediate velocities on global average of about 40 millimeters per year. Now, these latter two factors make this one of the warmest end members of subduction globally. And what that means is we get dehydration of our downgoing oceanic lithosphere at about the shallowest depths we can get for this eclogite transition, the main water producing metamorphic reaction that takes water out of our downgoing slab as it moves to eclogite. And this can, when you're releasing water at these depths, this can significantly affect the seismogenic properties of the plate interface itself. And I want to stress that these are fluids that are being released from these metamorphic dehydration reactions. These are not fluids being released from things like the closure of pore space and sedimentary rocks. We think that happens mainly at shallower depths, shallower in about 10 kilometers. So this is taking hydrous mineral assemblages down to pressure and temperature conditions where they are not stable and they undergo dehydration. Now, we think this is manifest mechanically through the presence of intraslab earthquakes. We have this volume change associated with this dehydration that leads to embrittlement and allows for failure within the plate, within the downgoing oceanic lithosphere. Now, if these fluids that are created through this dehydration are able to escape from that plate, concentrate near the plate interface, this can lead to the buildup of pore fluid pressures. Get this laser pointer back. This can lead to the buildup of these pore fluid pressures below some impermeable plate boundary. And in particularly warm subduction zones, this leads to a process that we call episodic slow slip and non-volcanic tremor. So if you're not familiar with these processes, we have our little geodetic station shown here in our forearc. We have something that looks very much like the seismic cycle. We have our buildup of strain along the plate interface leading to a GPS station moving toward the continental interior over time. And then we see this strain release that we think is taking place along the plate interface. So we get this trenchward, this reversal motion of that GPS station toward the trench, but opposed to the seismic cycle where this motion takes place over periods of seconds. This takes place over periods of days to weeks or even longer in some subduction zones. In Cascadia, it's about a 2-week period. that we see these GPS stations moving trenchward. And this occurs at the same time as we see basically an increase of noise on our seismic stations that are distributed throughout the Cascadia forearc. But if we look at this increased noise on an array of stations, we see that this is actually a coherent signal generated from failure, we think, near the plate interface, and we call this signal non-volcanic tremor. Now, some people think this non-volcanic tremor is composed of a lot of very small low-frequency earthquakes, This, again, very similar, we think, mechanism for generating them, the buildup of very high pore fluid pressures beneath an impermeable plate boundary, which eventually reaches some critical pressure that allows for this transitional slip behavior between the locked portion of our plate interface, further up dip, and the stable sliding zone, further down dip. Now, of course, we can release fluids deeper than this as well. If we release these into the cold part of the mantle wedge, this leads to serpentinization, even deeper. If it fluxes through that convecting hot portion of the wedge, it leads to flux melting and the generation of our volcanism in our overriding plate. Now, for this talk, I really just want to focus on these seismogenic phenomenon. And I'd say this is a pretty good conceptualization in 2D of what a particularly warm subduction zone looks like, but the real Earth is much more complicated than this, which is good for all of our job security. So we can look at the overriding plate. Some of the most striking variations we see in the Cascadian margin to first order is we have this variation in the basement compositions in our overriding plate. The central and northern portion being dominated by the Silesia terrain, this over-thickened oceanic crustal terrain, and the southern portion being characterized mostly by this Klamath terrain. This is the ocean island arc, along with some oceanic lithosphere that was accreted onto the margin in North America somewhere around 100 million years ago. You can fact check me on that date, but much earlier than Silesia accreted. We also see significant variation in the distribution of these intraslab earthquakes. See that it's mainly localized to the northern and southern margins of Cascadia, very little intraslab seismicity shown in central Cascadia, at least over this period of about 25 years from the USGS catalog. So this correlates really well with this distribution of non-volcanic tremor along the margin and these shorter durations of slow slip recurrence intervals. And you might say, okay, what's so interesting about this? You just told us these are both fluid mediated processes. So we would expect things like this to correlate. And I'll say that's true. But I will say that I think the relationship between these is actually a little more complex than you might guess at first order. And we'll go through that in a little bit here. We also have no reason to expect these processes to correlate with things like Bouguer gravity anomalies. For instance, we see that in areas that have high amounts of non-volcanic tremor and intraslab seismicity, we also have these relative Bouguer gravity lows shown by these warmer colors in northern and southern Cascadia. Now remember, Bouguer gravity tells us about mass deficits below basically sea level. There's no reason we should expect intraslab earthquakes or non-volcanic tremor to have significant perturbations to our density structure along some margin. We see that it also correlates with uplift rates along the margin. So this is the background is from a plate locking model predictions, and the little circles are GPS stations, tide gauges, and leveling surveys. We see that uplift is highly focused along the northern and southernmost portions of the Cascadia forearc. And of course, if you have some anelastic contribution to this uplift that outpaces your erosion, you're going to build up differential topography over geologic timescales. We see these higher, more elevated portions of our forearc in northern and southern Cascadia relative to this central portion. So the goal of this talk is to try to figure out what physical mechanisms can relate these different observations to each other. I want to first start off by just focusing on these seismogenic phenomenon. And in order to understand what's going on near the plate interface and how this might communicate with the surface, we need to create a model of seismic properties that can accurately recover large changes in seismic properties over relatively small spatial scales. For instance, we know that the crust is the most seismically heterogeneous layer on Earth, just strictly due to variations in composition. When you start adding water to it from these dehydration reactions, you get another free parameter that can really affect the seismic properties that you're recovering. So in order to do this, we're going to combine two passive seismic techniques. The first uses Rayleigh waves derived from ambient noise measurements. Now, the benefit of using this method is it's sensitive to the absolute shear wave velocity structure in the Earth where these waves are propagating. And that's really useful when we're trying to investigate areas where we think fluids are playing a role, because fluids are going to affect our shear waves more than they're going to affect our other types of seismic waves. Now, the shortcoming of this methodology, though, is these Rayleigh waves have very broad sensitivities to shear wave velocity as a function of depth. So what you're seeing here is the sensitivity kernels of these different Rayleigh waves. Let's say for some a Rayleigh wave, you get a velocity for a period of 8 seconds that's sensitive to the average shear wave velocity between about 5 and 25 kilometers depth. So if there's any discontinuity, velocity discontinuity in that depth range, you're not going to see it well by using these Rayleigh waves. But we can pair this with another data set that's very sensitive to these velocity discontinuities, and that is receiver functions. And specifically, these are P-wave radial receiver functions. You can see the response of the receiver function shown in red to that same shear wave velocity structure shown there in black. You get this nice positive amplitude peak, whose amplitude corresponds to the magnitude of the velocity change across that boundary. Now, the shortcoming of this methodology is it's not sensitive to the absolute velocities on either side of that boundary, only the velocity contrast across it, but it can be complemented by those ambient noise measurements to constrain those absolute velocities. So we can use these data sets and join them in a inversion to create a 3D shear wave velocity model that is sensitive to both absolute velocities and depths to discontinuities without having to assume any a priori structure in our starting model. So that's really powerful because that's a big shortcoming for a lot of tomographic imaging techniques. Usually you need to use some a priori information to get a realistic recovered structure. This, using these two data sets, significantly mitigates that issue. If you have some discontinuities that you think are well constrained, you can impose them, but if those are wrong, it's going to map erroneous structure into your final model. So I'll show you conceptually how we go about doing this. The first thing we do is create a 3D model of discontinuity structure throughout our study area using adaptive common conversion point stacking. This is analogous to common midpoint stacking if you're using controlled sources. And what you can see here is this nice positive amplitude peak in the receiver function that corresponds with an independent estimate of crustal thickness, or the depth to our MOHO boundary. So we see that we're recovering this really well using this 3D, by creating this 3D discontinuity model. We also see this dipping positive amplitude anomaly that comes in about 1 second in PS time after independent models of where the Wanda-Fuka slab is. In PS time, 1 second is about 8 kilometers. So what we're probably imaging with this dipping positive amplitude anomaly is the MOHO of the downgoing oceanic lithosphere. So we can take this discontinuity model, we can combine it with our ambient noise Rayleigh wave derived Rayleigh wave dispersion data, plug it into a starting model that's a simple half space, 4.5 kilometers per second down to the base of the model, discretize into 1 kilometer thick layers because that's about the theoretical resolution of the frequency content in the receiver functions that we're using, and impose no constraints on where structure should come from in this model. right? So this starting model might as well think we're back in West Lafayette, Indiana, in the middle of our craton. It has no idea what the tectonic context of our environment is. But when we simultaneously fit both of these data sets, we recover a final model that looks like what we would expect it to look like for a subduction zone. That's always promising. So first we see that we have this transition from yellow velocities, things that are consistent with crystalline crustal material, transitioning to these blues, consistent with mantle lithosphere, corresponding with that independent estimate of crustal thickness. So we're recovering our crust mantle transition really nicely in our overriding plate. We also see this dipping fast velocity feature right below estimates of where our slab is located. Okay, so now we do this for throughout the entirety of the Cascadia forearc to create a 3D model of shear wave velocities. Now let's look at the structure in these areas that are experiencing particularly high amounts of non-volcanic tremor. Here's a cross section along the northern part of Cascadia, kind of runs through the Olympic Mountains up here, below the Puget Sound and across Seattle. The most striking feature we see in this cross section is the presence of this very low velocity zone feature that parallels the downgoing oceanic lithosphere, but clearly lies in the lower crust of the overriding plate. You can see that it spatially corresponds extremely well to the surface projection of non-volcanic tremor, indicating that these are related. Remember that this is a fluid-mediated process, and the velocities we're seeing in this low velocity zone get down to about 2.8 kilometers per second. This is much too slow to be attributed to crystalline crustal material at these pressure and temperature conditions. So it really necessitates the presence of fluids to be driving this low velocity zone that we see corresponding with our distribution of non-volcanic tremor. Now there's been some active source imaging that's done just to the north of the study area. Many of you are probably familiar with this data set, but they see that they image the same low velocity zone. They've kind of inverted the color palette here. So reds are faster than yellows. So they see the same low velocity zone. And they also see, based on the reflection imaging, that it's characterized by this highly internally reflective package of material. In the Cascadia literature, this is called the E reflector or the E layer. And it's generally interpreted as these underthrusting sediments beneath the Cascadia margin. Now, given the PT conditions that these are likely metamorphosed, something more akin to a schist than a sediment, as we would traditionally think about it offshore. And given the velocities that we're seeing, these likely have fluid within them. Okay, now we can look at our other region of very low shear wave velocities in southern Cascadia, and we see pretty much the same velocity structure, very low velocities in the lower crust of the overriding plate that spatially correspond really well with the surface projection of tremor along the margin. This is a 3D model, so we can look at these in map view as well. Here's a map of average shear wave velocity in the lower crust of that overriding plate. See a really good correlation between these regions that show high tremor density spatially and these low velocities, where low velocity, I would say at these depths, is defined as anything lower than about 3.2 kilometers per second. That'd be about the slowest we should expect for any crystalline crustal material, even given extreme amounts of anisotropy. So anything that is yellow or warmer is anomalously slow for the depth range that we're looking at, corresponds really well with this distribution of tremor. We can also look at the thickness of these packages. We see that they can be about 10 kilometers thick in many places. And this is important because other people have seen these low velocity zones in previous literature and interpreted them to represent just oceanic crust. And based on Shuoshuo's imaging, we know that offshore Cascadia, the crystalline portion of the Juan de Fuca crust is only about 6 kilometers thick. So this has to include more than just oceanic crustal material. And I would say, given the reflection images we see, this is probably dominated by sedimentary material rather than oceanic crust. You see this really good spatial distribution between where these low velocity zones are particularly thick in our distribution of non-volcanic tremor. So we interpret that along northern and southern Cascadia, we have these zones of underthrusting sediments beneath the margin that are being infiltrated by the fluids that are causing non-volcanic tremor, this transient slip behavior near the plate interface. So full disclosure, I'll show you a cross section from central Cascadia as well. This area where we don't see significantly thick low velocity zones and we have very muted non-volcanic tremor. This is what that cross section looks like. You can see we have these yellows extending basically all the way down to the plate interface. These velocities are consistent with that Silesia terrain crust, this mafic terrain extending all the way to depth. So no significant evidence for sedimentary underthrusting in central Cascadia. Now, if you're familiar with the Cascadia literature, you know that Anne Trehew saw this in the kind of early to mid 90s, that in central Cascadia, where the Silesia terrain is the widest, it looks like it's also the thickest, extending about 30 kilometers to the plate interface, thinning as we move northward. So in northern and southern Cascadia, we have these thick packages of underthrusting sedimentary material that are being infiltrated by these fluids. While in central Cascadia, it looks like that Silesia terrain extends all the way down to that plate interface. Now, do we have other evidence that this stuff that is underthrusting beneath the margin, these low velocity zones, are in fact sedimentary rocks rather than something like oceanic crust? And I think that's where we can look at that Bouguer gravity and see this really nice correlation between locations where we have relatively low Bouguer gravity, warmer colors are lower Bouguer gravity, and these thick packages of underthrusting sedimentary rocks. We see it really well in the south, but we also see it much higher resolution than I would actually think based on the data set we're using. You see that right as the Silesia terrain turns this corner, kind of becomes a little thinner, you get this lower Bouguer gravity anomaly. Corresponds really well with where we start picking up this low velocity zone having a significant thickness, again, further to the north. So how does this relate to the distribution of tremor? Ray Wells and others put forward this hypothesis in 2017 that in these areas where we have these thick zones of underthrust or basally accreted sediments, these act as vertically impermeable boundaries, so we can more easily build up our pore fluid pressures, in these southern and northernmost portions. This is scaled to that to this map view, more or less. So we can build up those pore fluid pressures that seem to be necessary to enable this non-volcanic tremor and episodic slow slip in these regions. While in central Cascadia, Silesia extends all the way to the plate boundary. And we don't build up pore fluids pressure as fast here because they invoke that we have these kind of enigmatic forearc faults that are able to tap that plate interface, relieve some of that fluid pressure, not allowing it to host as much of that transient slip behavior. And I think it's a pretty good hypothesis, but I would say it's very overriding plate focused. This doesn't explain why things deeper in the subduction zone should also correlate with what we're seeing in kind of the plate interface to surface properties. Okay, so it seems like this non-volcanic tremor correlates really well with these regions where we have thick packages of underplated sediments beneath the Cascadia margin. These things are slow because the fluids that are causing non-volcanic tremor are able to infiltrate into these basally accreted packages of material. Further evidence for these being sedimentary in origin comes from the correlation between the thickness of these low velocity zones and Bouguer gravity, should say relative Bouguer gravity lows. They're not necessarily negative. But none of this explains why these should correlate with something like intraslab seismicity. So now I want to turn our attention to what could control intraslab seismicity variations in along the Cascadian margin. Because if these are acting as a proxy for where we're releasing fluids, right, this is going to have, this would explain the correlation with non-volcanic tremor. And I want to walk through kind of two end-member hypotheses for why intraslab seismicity is distributed in the way that it is. And the first one, I think, would be most people's kind of gut reaction to seeing this is, oh, well, what we're seeing is that the downgoing oceanic lithosphere is variably hydrated prior to being subducted. So this is going to be primarily controlled by deformation that takes place in the Juan de Fuca plate prior to subducting. Let's look at some proxies for deformation in the Juan de Fuca plate today and see if these can be projected further down dip into the subduction zone to explain this seismicity distribution. So first thing you could look at just as a proxy for deformation is seismicity offshore. And to first order, what we see is it shows decent agreement. We see that the Gorda segment seems like it hosts a lot, well, it does host a lot of earthquakes. If you use that as a proxy for deformation and therefore at least the creation of transient permeable pathways for these ocean fluids to percolate down into our oceanic lithosphere, we would expect this portion of the margin to be more hydrated. So maybe that could explain what's happening in southern Cascadia and why we have so much intraslab seismicity. But we don't see that amount of significant amount of intraplate seismicity, interplate seismicity in the Juan de Fuca plate further to the north. Makes it kind of hard to use that to explain why we have so much seismicity in that portion of the margin. And if we go look at the Cascadia Initiative OBS data, we actually see that at least during the period where those offshore broadband seismometers were deployed, there actually wasn't much of a difference in the rate of seismicity between the southern portion of the Juan de Fuca plate, the Gorda segment, versus the central Juan de Fuca plate. So this begs the question of maybe that catalog is a little biased by using onshore stations to record these earthquakes offshore, or maybe these earthquakes aren't a direct measurement of hydration. We can't use them as a proxy for hydration in the Gorda plate. We can also look at some other proxies for deformation along the margin. This is from Shuoshuo's work. And we see kind of the opposite of what we would predict based on what's happening further down dip. In northern Cascadia, we see, if you want to interpret these as deformation, that most of that deformation is constrained to that crustal portion of the oceanic plate. Now, the mafic material is not good at hosting water, right? Our basalts can hold maybe 3% weight water when fully hydrated. Gabbros are less than 1%. This is not going to transmit a significant amount of fluid down into our subduction zone. And if we look in central Cascadia, in this area where we have quite a bit of seismicity based on that Cascadia Initiative data, we see these apparently moho busting faults. Now, if you can get fluid down to mantle peridotite, that can hold 12% weight water when fully hydrated, 4 times more than our basalt, and also volumetrically much more significant, right? We have a lot more peridotite for our mantle lithosphere than we have oceanic crust. So that would be a more effective mechanism to take fluids down into the subduction zone. But what we're seeing is we don't have much seismicity in central Cascadia, right? Whereas this would imply that that's where the bulk of the seismicity should be occurring if that seismicity is driven by that dehydration and brittlement mechanism. We can also look at upper mantle PN waves, so upper mantle refracted P waves. And we see the opposite of what you would expect. Again, we see that in the Gorda segment, the velocities we recover are consistent with half-space cooling predictions for a dry peridotite, shown by this black line, right? Very close observational velocities relative to half-space cooling predictions, except when you get near the Mendocino triple junction. But when we look at the Juan de Fuca plate, sensu stricto, this northern portion, we do see a significant decrease in P wave velocities in the upper mantle from that half-space cooling prediction. So you can interpret this change between predicted and observed as evidence for an amount of hydration, an alteration of that upper mantle. Serpentinite, what we get when we flux a peridotite with water, much slower than a dry peridotite. You can also look at this refraction line, goes from south to north along the Cascadian margin, again seeing the opposite of what we would expect given seismicity down dip. In kind of the central portion, we have more evidence for hydration if you just map velocities straight to hydration. Then we get to the north where we have faster velocities in the lower crust of our oceanic lithosphere. So I'd say that variable hydration due to deformation that occurs prior to subduction does not seem to correlate well if it's projected down into the subduction zone. I don't want to speak in absolutes, so I'll just put a question mark here. Many of you are involved in the KC data set. One of its explicit goals is to understand deformation in the Juan de Fuca plate prior to subducting in the margin. So we'll stay tuned. If this could be, maybe we're just sample biased, but I would say that like an analogy is we're in a jury, 11 people think someone's guilty, one person thinks that they're not. They have to overcome a lot of evidence to make the case that this is the controlling mechanism for what's happening down dip. So now let's go to this other end member hypothesis where things are uniformly hydrated prior to subduction. What this means is this intraslab seismicity isn't telling us about variable hydration, rather it's telling us about where fluids can actually escape from that downgoing oceanic lithosphere. We know based on thermopetrological modeling that differences in convergence rate and plate age are not enough to change that eclogite transition depth substantially. You might change it by a couple kilometers. Pretty much everything's dehydrating around 40 kilometers depth. So sourcing our fluid isn't necessarily a problem. It's getting it out of that downgoing oceanic lithosphere to cause the non-volcanic tremor that is the controlling factor maybe. So we can look at some evidence for this. Obviously, if you have earthquakes, these are going to act as these transient pathways. If there's fluids present and you create a fault, that fluid's going to take it and get out of that downgoing oceanic lithosphere. But we can also look at what these hypocenters tell us about slab morphology. So here's the slab model from Macquarie 2012. What we see here is that in northern and southern Cascadia, the slab seems much more contorted than what we see in central Cascadia. So we use this surface, we can calculate the curvature of the top of that slab. And what we see is in these areas that have significant amounts of intraslab seismicity, that the top of the slab is concave downward. So if you think about your kind of general intro geophysics elastic principle, if you have a stick and you bend it, the top of that stick goes into tension, right? And that's much easier to break than something that's in compression, right? We know that rocks in tension break at lower differential stresses than rocks in compression do. So the fact that our slab is contorted may be why we are more prone to having these earthquakes in the northern and southern portions of our subduction zone. Now, what could be driving the slab contortion? There's been some really nice teleseismic tomographic imaging done along the margin by Miles Bodmer and others that show these significantly slow mantle anomalies below our subducting Juan de Fuca slab. So here's our Juan de Fuca slab. It's dipping to the east. We're looking at average P wave velocity between 100 and 250 kilometers depth. In the northern and southern portions of the subduction zone, we have what they interpret as subslab buoyancy anomalies, basically upwelling asthenosphere below your plate that's pushing up on your plate, and then you can't curve back downward until you pass over those buoyancy anomalies. And that's how we get this a relatively shallow dip right above these low velocity zones, and then this very highly curved surface as we move further to the east. Okay, so let's bring this back into our picture that we talked about earlier. First, we have our subslab buoyancy anomalies. leading to shallow mantle dips directly above them. That's what these contours are. Northern and southern Cascadia have very shallow slab dips. So these subslab buoyancy anomalies seem to be modulating slab morphology. When we calculate the curvature associated with these, we see that that curvature correlates really well with these regions that have higher amounts of intraslab seismicity. So these intraslab earthquakes are representing basically increased permeability for fluids that are present in the downgoing slab to escape and propagate up to the plate interface, where they can cause increased amounts of non-volcanic tremor and slow slip. So now we kind of have a perspective on what's happening in the subsurface that can link together these different observations. But how's this to relate to what we see at the surface? How does this relate to uplift and forearc topography variations that correlate with all these different features? So there's been some really nice thermomechanical models created for the basal accretion process. When we evolve this model, what we see here, orange is sediments, pelagic or heterogeneous, green is our oceanic crust, basalt in dark, gabbros in our lighter green. As we evolve this process of basal accretion, what we see is this domal exhumation of material above our downgoing plate, leading to these kind of anticlinal structures of intercalated basaltic slivers, shown here as these darker colors, and these predominantly sedimentary rocks. Now, assuming your exhumation can outpace your erosion, you're going to build up a topographic high immediately above the locus of basal accretion over geologic time. Nice thing about this is it creates some geologic observations. We can actually go out into the field and look for evidence of this process by looking at the rocks. And I'd say we have evidence for this process happening in northern Cascadia, mostly coming from structural mapping, but also coming from low temperature thermochronology. So we can look at exhumation rates in the Olympic mountains, the accretionary complex that's exposed at the surface. We see this really characteristic bullseye pattern associated with the Olympic mountains, where we have high exhumation rates, more or less where we have our highest levels of topography. So we can digitize this, we can overlay it on our shear-wave velocity model, shown here in green. And we see that the high exhumation rates correlate really well with these zones that have these very slow shear-wave velocities at depth. So if we were to take this shear-wave velocity image and put it in the context of that thermomechanical model, show it to a geologist, it might look something more like this. These low velocity zones represent areas of active basal accretion of material from the downgoing plate to the overriding plate that are being infiltrated by these fluids that are causing tremor and leading to uplift and a topographic growth in the overriding forearc. Okay, so how do these relate? All right, so we have basal accretion causing increased uplift in northern and southern Cascadia. These areas where we have thick packages of sedimentary material are corresponding with increased amounts of this process leading to that topographic growth. Now, how might this relate mechanistically to tremor, right? We already showed that there's this observational correlation between these two, but why should we have increased amounts of basal accretion in these regions that are experiencing higher amounts of non-volcanic tremor? So I want to point out one thing in this map. Here we have low frequency earthquakes. We think these are basically just large tremor events, but we can actually locate the hypocenters of these. We can't do that for non-volcanic tremor because we don't really know the origin time, so you can't constrain that depth versus origin time trade-off. That is always a problem in earthquake location. But with low frequency earthquakes, we can see clear body waves associated with them, and we can locate their hypocenters. So we see that these basically occur at the down dip edge of our very low velocity zone. So this tells us that this portion of that plate interface, which we can assume from tremor as well, has a lot of fluid around it. If you have a lot of fluid, that's going to weaken the material near that plate interface, perhaps making it much easier to transfer from that downgoing plate onto that overriding plate. So it seems like these areas where we have a lot of fluid, if we use tremor as a proxy for fluid, allows for the more efficient transfer of material from that downgoing to that overriding plate, more efficient basal accretion that is reflected in the surface expression of subduction along the margin. I'd like to point out that Cascadia is not the only margin that has these regions of elevated forearc topography. We see this actually in a lot of subduction zones globally, Nankai, Alaska, we see it in Hikurangi, we see it in Chile. And one thing to note is basically all of these margins also have deep non-volcanic tremor associated with them. That fluid at these kind of intermediate depths, which may allow for enhanced basal accretion and therefore drive this uplift of your forearc topography. Now we can also look at seismic images from these other margins, and it looks like we see significant amount of evidence for basal accretion when we look at these margins. The most correlative example is probably from the Alaska margin. This is a very similar methodology done by Kevin Ward and Fan-Chi Lin. And you see the same zone of very low velocities in the lower crust of the overriding plate, paralleling this downgoing Pacific oceanic lithosphere, lies right below the Chugach terrain, this forearc high that has some of the highest exhumation rates that we see, about 4 millimeters a year in the Chugach terrain of exhumation. You see this in central Chile, kind of a finger of slow velocities ascending to about 50 kilometers depth, beautifully shown in reflection data in Nankai, where we have these what are interpreted as duplexed sedimentary packages. And it's also been interpreted beneath the Rukamura Peninsula based on seismic images and low temperature thermochronology at the surface. So this basal accretion process might actually be a pretty common process occurring, at least in these particularly warm subduction zones. And the important thing about this is a lot of times we create these locking models that assume that a lot of the uplift that you're seeing on that overriding plate is part of the seismic cycle. But this is going to be an anelastic process. It's going to be driving uplift without necessarily telling you about coupling at the plate interface. So it's definitely something we should be aware of as we move toward trying to solve for these more hazard-focused problems in these subduction zones. All right, so to wrap it up, there's a lot of variability in the Cascadian margin that seems to correlate with each other. We have these subslab buoyancy anomalies that control the morphology of our downgoing oceanic lithosphere, leading to increased amounts of slab curvature at the top of our subducting slab in the northern and southern portions of the margin. That may be the fundamental control on variations in that intraslab seismicity that we see. The seismicity creates zones of transient permeability where fluids can escape from that downgoing plate, percolate up and concentrate near that plate boundary to lead to the variations we see in non-volcanic tremor and episodic slow slip recurrence intervals. These fluids may make that basal accretionary process more efficient. So where we have increased amounts of tremor, we have increased amounts of fluids, and this leads to weaker material, the easier transfer of that material from downgoing to overriding plate. These are predominantly sedimentary in origin, mostly based on those reflection images, but that is also validated by variations in the Bouguer gravity that tell us that we have some lower density material near the plate interface in the northern and southern, or I should say in the below sea level, beneath the northern and southern margins of the Cascadian margin. This basal accretionary process is going to drive uplift, some of which is going to be anelastic and lead to the building of differential topography over a geologic time. All right, so with that, I'll wrap it up. Thank you for your attention.
Johnson, I have a question about the physical expression of those low velocity zones. I'm more an active seismologist. We've studied volcanic arcs a lot, and I mostly looked at compressional velocity structures to understand the nature of volcanism and the volcanic rock. But we always, and that works reasonably well, but what we then sometimes found when we look at shear waves is that the lower crust of these volcanic arcs sometimes has a surprisingly low VP-VS ratio, so therefore a high shear wave velocity. And some scientists have interpreted as meaning that there might be sediments underplating as they are subducting. Have you looked at VP-VS ratios here to identify these bodies?
So we looked at, yes, we did a little. We did Wadati-Benioff plots, basically using these intraplate earthquakes and these low frequency earthquakes. And we found that it is relatively low VP-VS on average for the crust, which is really interesting. That's about 1.75 or something for that basically surface down to where we have those intraslab earthquakes. Yeah, so really interesting. If we compare our shear wave velocities to active source images in these same areas, we generally see about a VP-VS of 2 for these things. So if you just like overlay different methodologies, which is not super rigorous, but we see that they're about 2. Yeah, so it seems like, I don't know, you can play some games with the like weighted average of VP-VS for the crustal column. But yeah, I guess that'd be my response. They tend to be about 2 if you just compare P-wave and S-wave tomographic images just directly.
Thank you.
Can you use this one?
Use this one. Hi, thank you for a really interesting talk. I was wondering, in your slab bending, the areas that have higher curvature, have you compared that to what you would expect of the focal mechanisms of the interslab earthquakes?
At some point I did. Yeah, these are really nicely shown by a paper by Kuko Wada. And I don't remember off the top of my head what they see, but a lot of this interpretation of the stress state is actually directly from that paper. So what they see is this area is, let's say they'd say less stressed, or there's lower differential stress in kind of the central Cascadian margin, whereas on the northern and southern portion, you have this higher amounts of differential stress. I don't remember the orientation of the focal mechanisms. I believe they're still kind of dominantly subduction oriented. Yeah, so we don't have significant, like, let's say, subduction perpendicular extension. See, everything seems to be in the plane of the subduction zone. Yeah.
Cool, thank you very much.
Hi, I have a really good talk and I have 2 questions. The first one is, it seems like you have linked everything together, and there's one part seems not linked, which is for the earthquake, you are trying to use the 2 like big kind of like in the mantle low velocity body for the bending of the curvature. And for the like the tremor, you are thinking about the silica like it's going to deeper. So what's the relationship between those probably 2 mantle low velocity body with the features silica in the lithosphere on the North America? And that's the first question. The second one is for the earthquake depths and the tremor depths in the north portion, it seems to be happens at a similar depths, but in the south portion, seems the earthquakes are happening shallower than the tremor. So what's controlling that difference here?
Okay, I'll start with the first one. How does the deeper mantle relate to the distribution of tremor in overriding plate architecture?
Yeah,
right? That's basically the. Yeah, so I would say this is an interesting question, and it requires a little more research, I think. But I would say to first order, the slab contortion is controlling intraslab seismicity, and this is basically telling us about flux out of the slab, right? So you have a higher flux out of fluids that leads to more fluid near the plate interface. And that leads to higher amounts of basal accretion in the areas where we have these high distributions of non-volcanic tremor. So one potential explanation is that this low amount of tremor in central Cascadia is long-lived. And at some point prior to the Celestia margin looking like it does today, it was, let's say, 30 kilometers thick everywhere. And we've just kind of had these two areas that are experiencing more fluid flux and adding more basally accreted material over geologic time. That's one explanation, right? Taking this to like long geologic timescales. The other one, which I would like to test, and I kind of think plays an important role that we don't talk about too much, is backstop geometry and kind of pre-existing size, right? So we can take what we see today. We have these kind of thin crystalline crusts in southern Cascadia and northern Cascadia. Celestia is about 15 kilometers thick, Klamath as well, until we get into this basally accreted stuff. Central Cascadia, it's 30 kilometers thick. What would it look like if we did that thermomechanical modeling with the modern margin for the efficiency of that basal accretion, right? So you can kind of test these two end member hypotheses where you either started the same architecture in the overriding plate and basically cranked up water flux in the north and south, saw how that evolved. Or you could play with, all right, let's say what we have today is very consistent with what we started with. What would that look like if we were to do some of those thermomechanical models? So yeah, it's not a satisfying answer, but it provides, I don't know, some good ideas for our NSF proposal.
Thank you. So interesting, Doc. I have a question here. So it's kind of taken for granted, right? That if there is a fluid escape along some permeable interfaces or pathways, there's a tremor. And it's probably a simple subject and well studied, but why and what is the physical mechanism behind the fluid migration at these depths of tens of kilometers and the seismic tremor? Because we're studying fluid flow in the shallower sediments, right, in the sedimentary basins, which is like several kilometers below seafloor. And it's simply fluid migration that doesn't create much of anything. But at these depths, there must be enormous energy releasing, right? With fluid flow escaping. Is it like such an instantaneous process or?
That's a good question. I don't know if we have an answer for how fluid is percolating at these depths. My intuition would be that this fluid would kind of be a diffusive process, right? Where on long time scales, we're supplying fluid at, let's say, a constant rate. That would be how I would think about fluid flux in. The process that drives tremor and slow slip, we think is, well, one of the main hypotheses is this fault valve, where you basically have this impermeable boundary where all these fluids, they slowly percolate in and they build up over time until you reach some near lithostatic pore fluid pressure. And whatever that does, that allows for this transient slip behavior. It basically alters, let's say I don't want to say rheology, let's say the practical rheology, how this could be modeled in like a rate state friction regime. But yeah, I don't think we know well about how fluid is actually migrating at these depths. And I'm not sure we would see it depending on the scale of this fluid release.
It's sort of something close to hydrofracturing at a larger scale.
Maybe, yeah. So that's like the first interpretation of non-volcanic tremor ever, was that we're just hydrofracking everything at those depths.
Right.
I think the fact that it correlates so well with the slow slip, which is this geodetic measurement of actual slip along the interface, kind of made people push back against that hypothesis, because it's clear that we're accommodating shear when we have increased amounts of tremor. And now people generally think that tremor is just composed of a bunch of little low frequency earthquakes. It's relatively compelling evidence out there, but that doesn't mean it all has to be. And if you go, actually, I went to Greece with some metamorphic petrologists in April. And we were looking at the subduction complex exhumed from blue schist conditions. And what you see is you see these huge quartz veins that are shooting across foliations So there must be some component of fracking. And I think that's actually what we're seeing with these low velocity zones, right? We see these low velocity zones, and the fluid that's causing the tremor, maybe during a slow slip event, is able to frack in to that material, and then it gets stuck in that kind of foliation of those basally accreted sediments. So maybe that's more of a discussion we can philosophize about later. I'm not sure that answers your question.
No, great, thank you.
Really enjoyed your talk, thank you. The sub-slab buoyancy. Some of us have suggested that along the Gondwana margin in the late Paleozoic, there was an interaction between a large plume and the downgoing slab that resulted in flat slab subduction and tractions way into the interior of the supercontinent. And it's been suggested that this process of plume slab interaction has happened in west of Yellowstone, for example. Would you ascribe this sub-slab buoyancy to here? I mean, are we talking plumes?
Yeah, so first I'll do my best to interpret what the authors that originally interpreted that said. I think they do attribute it to basically higher flux at the mid-ocean ridge, getting kind of entrained in the mantle flow. So I think there's like a little hot spot along the ridge in the north, and the stuff kind of moves along with it, as well as in the south. So hopefully I'm interpreting what they're saying right. But yeah, there would be some like basically mantle anomaly a little closer to the ridge that would source these things, yeah.
Thank you.
Now it's 11:36, and thank you everyone, and thank you Jonathan for this excellent talk. And yeah, let's give another round of applause.